Hi everyone. Again, this is the last day of this introductory course, and today we are going to be dealing with a specific type of qubit implementation. And in this case, we are going to be seeing qubits using trap ions, or concretely just one trap ion. So this is the last day, yeah. Um, so at first, we are going to revisit few concepts that we have already seen, but that will be very fast, like the quantum bit or density matrix. After that, we will go into more difficult things, like such as quantum state tomography, and how do we read qubit state in the system. Also, after that, we will do the classical and quantum treatment of the movement of the trap ion in the trap, right? I will explain this better. And in the end, we will see a little of the experimental setup of in order to trap the ion, and also some results, because this whole thing was related to my undergraduate thesis project that I finished a few months ago, and we did get some results and stuff. So just to show something about these experimental results. So let's get started. Yeah, so the quantum bit, we already know this. We have our classical bit, right? That can be either 0 or 1. And our quantum bit is also called qubit, and it's just represented by any zero Hilbert space, by any bidimensional Hilbert space, right? Any general linear combination can be written in this way. And it's important to have the normalization condition that we have discussed a few times in other lectures. We can write the very same general vector using the other coordinates that are these angles here. With these coordinates, we can see the the states, also how the operations work in the Bloch sphere that we have also discussed in a few lectures, right? This is just to remember a few things. So what we are going to do now, and I know this slide has a lot of things, but I will explain step by step, is we are going, in this case, we're going to be working with an ion of calcium, right? Concretely, 40, calcium 40. This will be the ion that we'll be using. So the idea is to trap the ion using what is called linear pole trap. I mean, there are different types of ion traps. So the one in the picture is the one that we were using in the experiments, and in this case, this is a linear pole trap, right? So we are going to be trapping the atom in this trap, right? So uh, when we trap the ion, when we have it inside our trap, and it is stable, let's say, we are going to be playing around with wait, this should be another line. Well, doesn't matter, with the energy levels of the outer electron that is inside the atom, right? I mean, this ion here is going to have like an outer electron, that is going to have different energy levels, right? So we are going to choose uh, two of this branch of energy level, because we are going to have like a lot of different energy levels, but we are going to choose two energy levels, and we are also going to discuss in more detail this later. And we are going to call an energy level, and one of the energy levels state 0, and the other one state 1. So in order to so that's the idea. You trap your calcium atom, you have one outer electron, and with this one outer electron, you choose some energy levels and call it your 0 and 1 state, right? That's the idea. So after that, how can we manipulate the state of our qubits? So in order to do that, we just use lasers, right? We need to use lasers. And in the end, in the treatment that we are going to be doing here, the lasers are just going to be uh, mathematical or physically uh, modeled as uh, electromagnetic or electric wave, right? This is, I mean, for if you don't know much about wave in physics, this might seem a little weird, but this is just basically a playing weight in the sense that you have an amplitude, and this is just a constant, a vector constant can be three-dimensional, and this is just a periodic function, in this case the cosinus, right? So in here you have the frequency of your laser. This is the frequency of your laser, the time of the pulse of your laser, because you can have a certain time pulse, right? Or certain, yeah, I mean 5 seconds time pulse or whatever. This is also a vector that gives you the direction of the laser, right? So the propagation of your weight of your wave, and this is just a phase. Uh, Normally, you always add a phase in case. I mean, you can depending on this just depends on the initial condition of your laser, right? It's not. I mean, it's going to be important for us, but it just has a special physical meaning. It's just a phase in depending on the initial conditions. So the idea is just that we are going to manipulate the the electronic state of our outer electron using lasers, different lasers, right? We will need different lasers for doing different type of operations that we will also discuss later. So one thing that we will more or less see later also is that if we have here the phase of the laser, right? We can find a relationship between the phase of the laser and this angle here, right? And we can also find a relationship between the time of the laser pulse and this angle in the Bloch sphere. So this means this is just, and the relation is given by this rotation here that we will also try to explain a little more later. How do we came up with this? But using the laser, you can apply this rotation to the to the state of your qubit, in the sense that you are changing the electronic states of your outer electron, right? Because at the end, this zero is just this electronic state, right? And this one is just this other electronic state. Mhm. So applying the laser, giving a certain initial phase of the laser, depending on the time pulse, the length of the time pulse, we can move through through all the states that we want in the Bloch sphere, right? So that's important. But there is one more thing. This parameter here is a constant, and it's called the Rabi frequency, and it's a very important parameter in the experiment that must be experimentally measured in order to know this value. Uh, and basically, this Rabi frequency is a parameter that is related to the transition between, because since there are different types of transition between different types of energy levels, not every energy level is physically the same because they have this, let's say, different physical properties. So this Rabi frequency depends on the transition. Yeah, so that's basically, it's just a constant that will be measured experimentally, and is fundamental because if we want to properly control the state of the qubit, right, and that means doing this rotation, we have here the angle theta, right? So if we want to control the state of our qubit properly, we can control the time of the laser pulse, but we need to know the radio frequency, just because this angle is given by the travel frequency times the time of your pulse, right? So anyway, well, I wanted to say this at the beginning, but I forgot. So today's lecture is going to be, let's say, more difficult than the other ones since these are more complicated topics. So I know there is a lot of physics and everything I'm going to discuss. So it will be understandable that you don't get really a deep understanding, right, of everything that I'm going to say, but just try to get the ideas and concepts, and maybe in the future you can go deeper because I mean this slide was not so hard comparing to other ones that are coming, but anyway, I know it's not easy, right? So just let's try to take this lecture in a more I don't know easy way in the sense that things are more complicated, so well, it will be more difficult for you to properly understand things if you don't have a really good physics base, right? To understand some, for example, this wave equation, in order to work with the electric field or stuff, are some things that you need to maybe take a time to understand why this is like this, right? So don't worry if you don't understand it because it's not that easy, right? So now let's remind a little about the density matrix. And the density matrix just it was basically just a linear operator, right? That you can represent as a matrix. You have, and remember that we have pure states. That a pure state is just any state in our Hilbert space, right? As any physical state that can be represented as a vector of the Hilbert space. And the density matrix, sorry, the density matrix is given by this get bra, right? Very well. We also have mixed state. A mixed state are physical states that cannot be described by vectors in our Hilbert space. I mean, you cannot find a vector here that describe a mixed state because they are described as linear combinations of density matrix, right? This will be the density matrix. Will be the probability to be in a certain state. Let's say, yeah, I mean, I did explain this the other day, but we have this one, this other one, right? So this will be the probability to be in the state given by this density matrix, and this will be the probability to be in the state given by this other density matrix, the density matrix. So this probability must sum up to one, right? And the density matrix must satisfy these properties here. That, I mean, it's just I'm not going to detail more about this because we have already talked in the lecture, but you can try to go deeper later on. So this, I also showed this, but this is going to be important for what I'm going to be saying in the next slide. So basically, uh, if we have, for example, this pure state, right? This is a pure state, just the general linear combination that we are used to see, right? So remember that the probability here was just the module of the coefficients, right? This will be the probability to be in the zero state. This will be the probability to be in the one state, right? So if you see, these probabilities are on the diagonal of, of our density matrix, right? And for example, if you create this, let's say, mixed state, when you have this probability of being in zero state and this other probability to be in one state, you have this density matrix, right? So this is here we have an important, let's say, detail. And these two matrices, right, describes for sure different states, right? Because they are different. In here, as you can see, the density matrix are not the same. But the probability to be in either 0 or 1 is the same. Because in here, in this state, the probability to be in state 0 is given by the modulo square of alpha and in here is the modulo square of beta, right? That's the probability to be either non-zero or in the state one. And in the mixed state, we have exactly the same situation, because in here we have the modulo square of alpha, probability to be in the zero state, and it will be the one the density matrix given by the zero state, and in here the density matrix to be in the one state. So in this pure state, for this mixed state, we have the very same probability to be in 0 and 1. Experimentally, at the end, we are going to be measuring probabilities, right? Or expected values, since everything is in quantum mechanics, you cannot exactly know the outcome, just can know the probabilities and expected values doing a lot of experiments, right? And repeating, and at the end you get some statistics, right? So we need something more than just measuring the probabilities to be in either 0 or 1 in order to properly know the state of our qubit, right? Because if we just measure the probability to be in either 0 or 1, we cannot know for sure if we have a pure state or a mixed state. And this means that we need some procedure to be able to calculate these non-diagonal terms. Because the only difference between the mixed state and the pure state is that we have non-diagonal terms, right? So here we go with, oh, something went wrong here. Here we go with quantum state, sorry, tomography. I don't know, here, so, oh, tomography, yeah. Yes, so quantum state tomography. So this this is just a procedure, right, to calculate the density matrix of a certain physical system out of experimental measures. That's the main purpose of this. And there are for sure like a lot of different ways of performing quantum state tomography. And it's something that I believe is still on research for sure. They are trying to improve things because it's something that is not so easy. We are going to be discussing a little of the most known and basic methods of quantum state tomography, but the idea is the following. So we have our experiment, right? We have our experiment here. So out of our experiment, somehow, right? I will try maybe to explain this later. We are going to get experimental probabilities, and now I will be writing the probability in this way. I mean, this here is going to be the probability to be in this state, right? This is just, let's say, a change of notation, and this is going to be given by the trace of this projector, right? The projector that now I'm calling with this strange letter that is pi, right? This is pi, the big pi. So this is going to be the probability, and this just comes from remember that when I talk with the about the density matrix, I told you that you could calculate expected values using the trace of the operator and the density and the corresponding density matrix, right? So this is just using that result in order to get the probability. So if we have the experimental probabilities, we are going to be using, or I'm going to be talking a little about linear tomography firstly, and then I will maybe talk something about maximum likelihood estimation. That is another technique, yeah, more general technique, but in this case applied to the quantum state tomography. Very well. So in linear tomography, I don't know if this might take a while to to understand, but I will try to explain more or less. So the first step is just you write your supposed density, your unknown density matrix as a linear combination of a basis of matrices that of your space of matrices, right? Remember that when talking about vector spaces, square matrices can also be a vector space. So if you have a basis of matrices, you can write any square matrix. In this case, 2 times 2 is square matrix, and it might also be Hermitian matrix out of a linear combination of these matrices. So in our case, we choose this basis, and this is just the identity and the Pauli matrices. And this 1/2 here is just a reason for normalization using uh, this property, right? I mean, if we didn't do this, it would be a 2 instead of a 1, right? That's the only reason. That's not so important. So if we write the density matrix in this way, and this is just a linear combination, right? Of these matrices, we can calculate the expected value of these matrices in general, right? And this means this index here just indicates each of these matrices. This would be the trace of the corresponding operator, right? Because these matrices at the end, they are operators, times your density matrix. And if you plug this expression in here, right? This is just that. And using trace linearity of the trace and that stuff, you can take these coefficients out of the trace operation, and you can use this property here. And at the end, you get the coefficient, right? So I mean, if we calculate the coefficients, we know. I mean, we are going to know the density matrix since we know these matrices, right? This is just the Pauli matrix and the identity. So the only thing we need to calculate is this coefficient. And if we get to the point that we are able to calculate the coefficient, we will know the state, or I mean the density matrix. So calculating this expected value, we can calculate the density matrix, right? So the next step here is maybe a little more complicated, but you can write this operator in terms of their eigenvalues. For example, we know that the identity matrix, and in here also something I haven't said, I'm using the hat and using it in order to denote operators, right? Everything that has this hat over the letter is denoting a linear operator, right? Yeah, just notation. So we can write this as 0, 0 plus 1, 1, right? This is just the completeness relationship, right? Remember that. But for example, the sigma x or sigma z, maybe it's easier. It can be written in this way: minus, right? And this is just the eigenvector and the corresponding eigenvalue. I don't know if you remember when we talk about diagonalization and this kind of things, but we did discuss this a little. So you can write the vector, for example, the sigma x will be the corresponding x mass eigenvector minus x minus vector. And these guys are the same that when I was talking about up and down, right? In the sample of the Gerlach experiment. So, I mean, remember that we use different names, in a lot of different situations to call things that are very similar mathematically. I mean, they can be physically different, but the maths under the hood are more or less basically the same. So that's why we use different names, but the calculations are going to be the same, right? So you can write these operators in this way. So using this relation, writing this in this form, we can get to this, to these equations here, where I have explicitly written the relation for every coefficient. I mean, we have just 4 coefficients. The only step ahead is just using this other relation of orthogonality. And this is just meaning that the probability to be either in one state or if is orthogonal state, and that's the meaning of this symbol here, the orthogonal state, if or is always 1. in this bidimensional case. So if you plug this into this equation at the end, you get that the first coefficient must be this one, and also the rest of the coefficient depends on the probability of we inserting states. And that will be the end, in the sense that the next step will be just to measure these probabilities experimentally, right? And in that case, in the moment that you have this experimental measure, you will be able to know the density matrix. So in order to understand a little, maybe graphically what we are doing, at the end, for each of the measure, we are just doing like, we are projecting over one of the axes of the Bloch sphere, right? For example, when we measure this probability, we are just projecting onto this axis, right? With the 0 and 1 axis. So doing three measures is enough in order to know the density matrix, since you are going to be determining a point in the Bloch sphere, right? This will be for the x plus and x minus, right? And this will be for the, oh my god, for the y plus, y minus state, right? So that's basically what we are doing in this case. So maximum likelihood estimation, I'm not going to explain in so much detail, but the thing is that this linear tomography method sometimes is not is problematic, since we can get some density matrices that are not physical, and they are not physical in the sense that they don't satisfy this property here. Okay, because in order to be a proper physical density matrix, any density matrix must satisfy these three properties, right? Using linear tomography, we will for sure get these two properties here, but depending on the probabilities that we measure, and that has to do with experimental error, right? Because when you measure something in your laboratory, it's going to there is going to be some experimental error. So depending on how good your probabilities are, you can maybe get some density matrices that don't they don't satisfies this property, right? So in order to solve this, we can use a maximum likelihood estimation. The idea is to parameterize the density matrix in a way that it must satisfy for sure all these three conditions, and after that, define a function that describes the likelihood between your measure and the density matrix. And when you maximize this function here, you try to find the maximum. That maximum relates to the point that where your density matrix corresponds to your experimental data, and that's the point where you say, okay, this is the density matrix that I'm getting in my experiment. So one interesting thing about this method is that it allows you to add more than three measures, and that can be interesting. Even though you don't really need more measures, you could add more measures in order to maybe solve some experimental problems that you could maybe have uh, in order to increase the accuracy of your calculation of the density matrix. So in here, for example, instead of measuring these three axes here, right here, you maybe try to do another set of axes that could be, for example, the diagonals in the of a square, and it would be a total of 1, 2, 3, 4, 4 axes, right? So that's for everything I want to talk about this, because it's a little more complicated. So this is good, right? But there is a problem, because in order to do this, we need to measure, right, different vectors. I mean, different. I mean, if our qubit is in different states, right? Whether it's the 0 state, or the x plus state, or the y plus state, right? And also happens the same in this case. So in our experimental setup, and this means in any trap ion setup, normally you can only know the probability to be either in 0 or 1, right? So in order to solve this problem, we need to apply this transformation to our qubit, and this means we need to do some laser rotations. But since I know that this is like confusing for sure and difficult to understand looking at this equation, the idea is that if I have a transformation, right, and this means a qubit rotation using lasers in our case, that takes the zero vector to the vector that I want to measure, I need to apply the inverse uh, transformation, right? Because, for example, here I have an example. If I have this rotation here that gives me this state, I need to apply the inverse rotation, and the inverse corresponds to the adjoint rotation, because what I want to do is take this vector basis and convert it to the 0, 1, right? This is what I'm doing here, converting the x max, x plus, and x minus basis into the 0, 0, and 1 basis. And this basis here is the one that I can measure uh, in my experiment. So the idea is, if I want to measure these guys here, the probability to be in either this x plus or x minus, I just rotate the system using the corresponding operation, and then I measure normally in my 0 and 1 state. That would correspond to the probability to be in either x plus or x minus, right? That's the trick. So we can do this for any other vector. I mean, this is just an example for deeper understanding. So I did, because we were not able to implement this kind of procedure yet in the laboratory. So in order to try to understand these things better, I did I did some simulations in the computer using Qiskit, and Qiskit is just some Python library for quantum computing, developed mainly by ABM. Right, you can check the documentation. There are a lot of tutorials out there. If you are curious about quantum computing, I highly recommend you to search about Qiskit in Google and find information, because there is a lot of information out there about Qiskit. But basically, what I did is using the fidelity, and fidelity is just if you have two density metrics of two different states, you perform this operation, and this operation is quite strange. I know we are not having the idea is not to properly understand this, but the funny thing is that if the fidelity is equals 1, it means that these density matrices are the same, and if the fidelity is lower than 1, it means that they are not the same. And for example, if you get fidelity of 0, it means, I mean, it's the worst in the case that they are really different from each other. So I tried using a sample state that I knew, and I tried to perform the quantum state tomography using some coding in Qiskit. And if you don't have any error, any experimental error in your circuit, like, because in the simulations I did not introduce any quantum error. So at the end, you were always getting fidelity near 1 using linear tomography, because linear tomography, I mean, the procedure is correct. So if you don't have an experimental error, you will get a good result, right? So that's what I tested using Qiskit. So now uh, let's go a little to understanding the how do we trap the ion, how do we, how we the interaction between the ion and the lasers and this kind of stuff. But especially the how do we trap the ion, right? So at the end we have an ion trap, right? The ion trap is basically what the name is very a good name, in the sense that it's just a trap for ions. I mean, our purpose is to create somehow a physical device that can trap ions. So ions, we know that is gas. In this case, this is our calcium ion. So they have electrical charge, right? In this case, it is a positive ion, right? So how do we trap ions? we are going to create a certain device, right? Uh, that can have, well, I'm not going to draw, but a certain device that is going to be producing a potential inside the trap, right? So this potential and is going to be an electric potential must satisfy certain properties in order to trap the ion. So the potential, the electric potential that we are going to be uh, using is this one that you have here, basically. So it's a for sure a three-dimensional potential since we live in a three-dimensional space without thinking about general relativity and stuff like that, right? So we live in a three-dimensional space, so we have a three-dimensional potential in our trap, and we have for in the movement in the x and y plane is different from the one in the z direction because we are applying different type of potential in these directions, right? So, but basically, the idea here is that in the z axis or the z direction, we are going to have a perfectly harmonic movement, right? And if you don't know what is an harmonic movement, just think about like for example a pendulum, right? In the sense that a pendulum is just something like this, and it is rotating, right? Doing yeah, I mean the pendulum will be doing this trajectory, right? All the time rotating in this point. So the ion, sorry, is just going to be moving uh, in free space, but I mean it's going to be trapped, but it is going to be somehow levitating by this potential in the trap, and it's going to be doing a harmonic motion for sure. And the harmonic motion is just basically moving from the equilibrium position, and this is going to be the middle, and it's going to be oscillating, right, around the equilibrium position. That's basically the meaning of harmonic motion, more or less. I mean, explaining this without the equations is not the proper way for sure, but that's the idea. And for the other axis, we have a more complicated motion, but in the end, I mean, if we do all the treatment, we get to the Mathieu differential equation that has some quite difficult differential equations to solve. I don't even going to try to speak about that. But at the end, solving everything and for certain values of the parameters, and that has to do with the physical parameters of your trap, like in the device, physical device, right? You can get to this solution for both uh, x and y, right? I mean, this u here is just either x or y. It depends. But, I mean, it's for both the directions. So what we get here is that we have harmonic motion here. I mean, just an amplitude and a periodic movement, but this is multiplied by another factor here, and that this is normally called micromotion. This thing here. So in what we are going to do in the next steps, we are going to be we are not going to be taking into account this micromotion because depending on the system, we can not it's sufficient if we don't take it in account because we can prepare the device in order to maybe do some corrections in this micromotion. And apart from this, we will also be focusing in the z-axis direction from now on. Right. Maybe I should go a little faster. Anyway, so moving to the quantum Hamiltonian, and this will be maybe the quantum treatment. So remember that the Hamiltonian is the linear operator that represents the energy of the system, and the Hamiltonian is the one that is going to give us the evolution of the system, and is the one that we are going to be the operator that we're going to use in order to study the interaction between the laser and the ion. That's, I mean, the Hamiltonian is like the fundamental thing that you need in order to start understanding things. So our Hamiltonian is going to be basically made out of three terms. So in one term we will have the electronic Hamiltonian. For this, we are going to do an approximation because if you don't know, in physics, we do a huge amount of approximation in order to get to some meaningful results. So as I have already said, and we will see in a few slides, there are a lot of different energy levels, but we are going to be working in order to be able to calculate some analytic results. We are going to be working in a two levels approximation, and that means that we are going to imagine or work like if we were working with just two levels, and this will be the excited state and the ground state of our two-level system, right? In reality, we have more than two levels, right? But in this approximation, we are going to be working with just two levels. So let's say that this is the energy level of the excited state. This will be the energy level of the ground state, and this will be the frequency that you use in order to get from one level to another one, right? And this is just the h bar Planck constant. So this Hamiltonian, uh, taking into account this energy difference, will be this one. And why do we have here the sigma multi-Paulis? Is also maybe difficult to understand, but I cannot go into all the details. So that's why I said at the beginning that I know there is a lot of physical things that you may not be understanding, since this needs more physics understanding or things. But just take it that try to get the main idea that all right, we are just taking an approximation of two levels in the electronic Hamiltonian, and we are going to be working with that in order to do the calculations. Apart from that, the motion of the ion we have discussed in the classical treatment, that at the end we are going to be having a harmonic motion. So in here we have, this is the harmonic, I mean the quantum Hamiltonian for the harmonic motion, and this is the corresponding Hilbert space for the harmonic motion. So I know this is also something that you will probably not be aware of, but just take it as it is because this is in order to explain this, we will need like a few lectures just to explain how this works properly. And in the end, we have the Hamiltonian of interaction, and this is going to be the most important Hamiltonian because in here we have our rabbit frequency, and also these are the laser, the parameters of the lasers, of the frequency of the laser, the phase of the laser, the time of the pulse of the laser that we have talked at the beginning, right? And this CC here, it just indicated the complex conjugate of this number. I mean, in order to write this, instead of writing this plus this, right? And just writing this plus the complex conjugate, right? It's just a way of writing the same using less paper, right? So that will be put here the complex conjugate of this number, right? So let's move on. So in order to try to understand what we are doing, so at the end, right, remember that where this is similar to when we were discussing multi-qubit system, in the sense that we have the vibrational states of our qubit, and this means that different ways of how the ion is oscillating, right? It can be oscillating this way, or maybe a little with less energy, maybe. I mean, this refers to all possible oscillating state of our system, and that is described by a certain quantum Hilbert space. So, and in the other hand, we have the electronic Hilbert space that is described by these two electronic states, right? So, the total Hilbert space that we are going to be working on is the tensor product of these two guys, similar to, so we can have N and maybe F, right? This will be maybe a state of the system. I mean, this is just in order for you to clarify. The laser is going to be interacting with the electronic state, right? That's going to be our interaction. So this is going to be this Hamiltonian of interaction is going to be a linear operator in this space here, right? Very well. So Oh my god. But we have 10 minutes or something like that. This slide here is introducing some more advanced topic in quantum mechanics. I would say, I mean, it's quite fundamental, but also more advanced for sure. So just to briefly speak about this, I mean, when you face quantum mechanics, uh, depending on the problem that you want to solve, it might be convenient to work in different pictures that they are usually called. And these pictures are basically distinct perspectives that you can use in order to maybe do the computations easily, right? So at the end, pictures are just mathematical, different mathematical ways of doing the same because the result at the end is equivalent. But for example, these are they are more pictures for sure, but these are three main pictures in that they are more common, right, to use. So we have this Schrodinger picture where the time evolution goes into the state vector, and the operator is constant in time, right? So if you do, I mean, I'm going to explain this very fast. So it's normal if you don't understand. So ask any question now or maybe later on the Discord or at any moment, right? So, but just to give you an idea. So in here in the Schrodinger picture, the time evolution goes to the state vector, and the operators they don't evolve in time. So if you calculate the expected value using the Schrodinger picture, at the end it would look like something like this, right? Over time. Remember that this is the evolution operator that we were discussing a little in the last lecture. Right, so that's for the Schrodinger picture. In the Heisenberg picture, we have that the state vector stays the same in the evolution, but in this case, the operator is the one that is changing over time. And if we see that if we calculate the expected value of the operator here, we get the very same expected value since the pictures are equivalent, right? The only thing is changing is that we are applying um, the time evolution to the operator instead of applying it to the vector, right? That's different. That's the main difference between Schrodinger picture and Heisenberg picture. There is somehow a intermediate picture that is also called the interaction picture, and this happens when you have, and this is useful better when you have a Hamiltonian in this way, that you have like this base Hamiltonian and this interaction Hamiltonian. So in this case, the state vector evolves in times using just the base Hamiltonian, this guy. So if you do this, you can see that the Schrodinger equation would look like this, and your operators in the interaction in picture, they also look like this, right? And in the end, uh, is equivalent to the Schrodinger picture if you do the proper calculation. So yeah, I mean, I'm not doing this calculation, and there are some calculations behind these equations for sure. So don't be afraid of not understanding this straight, uh, because I'm just saying this in order for you to understand what I'm going to say now. So in order to calculate things that we need for our experiment and to do the rotation and stuff, we are going to be working in the interaction picture, and this means that we're going to be studying the interaction Hamiltonian, and this Hamiltonian is this one, the Hamiltonian over here, but in the interaction picture. And this is going to be the interaction, right, of the lecture, interaction. And this here is going to be the H0 that oh my God, so yeah, H0 that I was talking here about in the interaction picture. So we are going to we need to evolve the interaction Hamiltonian using this base Hamiltonian. And this computation, believe me, is quite very difficult and need a few pages in order, and a lot of approximations in order to completely do the whole calculation. So, and I'm just going to show the result basically. So, an important idea here is that while doing all the calculation, at some point you define this parameter here, and this is called the tuning. And this is just basically the difference between the frequency of your laser and the frequency of the transition that you are that you want to excitate, right? Because and this is what just the frequency that you needed to change from the ground state or to the excited state of your two levels electronic states, right? So the tuning is just the difference between this laser frequency and the frequency of these two energy levels, right? So defining this the tuning, we can find that depending on the value of the detuning, we can make different approximations for the Hamiltonian. So in the case that we have the tuning equals 0, we can approximate the Hamiltonian into this Hamiltonian here. And this would be the Hamiltonian of interaction in the interaction picture. That's can be confusing, right? So since we are so so since the tuning equals 0 means that the frequency of the laser is equal to the frequency of the transition. This is normally called the carrier transition, and that's why the car here, because it's the carrier transition. So if you do the time evolution using this Hamiltonian, at the end you get this rotation matrix, and this is the rotation that we apply in order to manipulate the states of the qubits, right? So that's yeah, that's the rotation that I did right in the very second or third slide, and this is the type of laser pulse that we need in order to move along the Bloch sphere. And it's an important detail, but maybe more difficult to understand, is that we are not using this type of transition, and I mean with this kind of detuning, we are not moving through different motional states. I mean, with different oscillating states, right? To the using the Hamiltonian of the harmonic movement. Well, so if we use the tuning zero detuning, we are just going to be moving in the electronic states, but not in the motional states of the harmonic oscillator. And I mean, this means that, for example, another remark that I will show later a little in the experimental result is that if we have, for example, the tuning that is integer factor times the frequency of the actual movement, right? I mean, this is just this frequency in the z direction is just the frequency of the harmonic movement that the ion is doing, right? This harmonic movement or oscillative movement, if you want. So if the tuning is proportional to this, and proportional must be proportional like I mean, it must be multiplied by an integer in the sense that it could be plus minus or plus minus 2 or 3 or 4. It cannot be a rational number, for example, is what I mean. So you can find that there are another type of transitions in the sense that, I mean, this is called the carrier transition, but you can find, depending on this detuning, other transitions that you are also going to manipulate if you properly adjust the tuning using the frequency of your laser. So using these other transitions, you can move in these motional states, right? If you use these other transitions here. That's just take note about that. So right. We still have a few things to discuss, but maybe I will go try to do it more briefly. So right, in this picture, I'm just showing this is on Spanish, right? Because I didn't find time to make the picture again in English, but this is just what is called Doppler cooling. Doppler cooling. And this is also a sideband cooling if you want. Sideband cooling. Sideband cooling, right? So this is the atomic structure of the this ion, right? The calcium ion that we were working with. So we have a lot of level. We have one level here, and indeed this level had two other inner levels here, and all these letters, all these inner levels, they all have physical meaning. But in order to understand that, we will need like another few hours to explain that. A full course on atomic physics. So let's just leave it there. So basically, what I'm going to say is that in order to the states of the qubit are going to be this one. I mean, completely this one, I think, or one of the sub levels of this bigger level, and one of the sub levels of this other big level. Let's say. So these are going to be our state 0 and our state 1, right? Um, Remember that I'm not talking about this sub level in detail because it would be just more confusing, and I believe that you are struggling enough. So maybe let's just leave it in this way. So in order to trap the ion in a stable way, we need to use this transition here using this laser, right? These are just the wavelength of each laser in order to go to one energy electronic level to another electronic level. So we need this laser to perform Doppler cooling, and Doppler cooling is just a procedure that somehow we are able to lower the temperature of the our ion using this laser. And with this, I mean, lowering the temperature just means that you are reducing the oscillation, right? You are making it more stable, more confined in space. So that would be very important in order to properly trap the ion in the potential that we have discussed before. Also, we have this laser here that is going to be fundamental, right? Well, maybe another color. This laser here is going to be fundamental because it's the laser that we are going to be using in order to manipulate the qubit, right? Since it's the laser that corresponds to the transition between the 1 and 0 states. So this carrier transition that I have talked here, we have discussed a little here. We are going to be performing that transition or that interaction using this laser. So this laser is very important. And these other lasers are just for helping in other procedures, like in case that the electron goes to this unwanted level, this laser is just going to send the electron back to the level that we want him to be. So yeah, that's the idea. I mean, and here is just because in order to get the calcium ion, we need to photo ionize the calcium. So it's just the two lasers that in order to take one electron out of the calcium, get the calcium ion that we are working with. So I know this must sound like a lot at this point, but think that the idea is that we have this quite crazy scheme of the levels. We have a lot of different energy levels. If we have here two energy levels, we have here 5 or 6 energy levels. I don't remember. Yeah, 6. Yeah. Here we have another 4 energy levels. I mean, there are a lot of energy levels. So at the end, we choose the energy levels that we wanted for our qubit, and somehow that I will try to explain in the next slide a little more. We use lasers in order to cool down the atom and manipulate the state of the outer electron in the ion to be in the energy state that we want him to be, right? And that is quite a challenge, right? Because this is crazy in the sense that we are trapping an ion, and that's like insanely tiny, right? And apart from that, we are trying to control the energy state of the outer electron of the atom using lasers. I mean, it sounds. I mean, for me, I mean, even though I know how it works, it still sounds amazing, right? So, in order to do this, don't think that this is something easy to do for sure. In here, I have a scheme of uh, the basically the laser system that we have in the laboratory, and it's also for sure very complicated to understand because as well you see this scheme and you maybe I don't know you get ill or sick just at looking at this complicated scheme. But believe me, it works if you go to the laboratory and see the table directly. So I mean, this is on Spanish, right? This is just the main table, right? So I didn't change the names in the image. I didn't have time for that. But anyway, just a few things because explaining all this in detail would be impossible. I mean, I will need maybe half an hour or an hour to do that. So in here we have the trap, right? Our ion trap, ion trap. So this is the point where the ion is going to be, right? Trap, right? Is the place that we have our trap. So in order to do that, we need some special vacuum system that I haven't talked, and refrigeration, and a lot of very specific device for the experimental setup. But talking about the laser system, so we have quite a huge amount of lasers, right? Uh, this is a special system for this laser here, and this laser was the one that was going to manipulate the transition in the qubits 0 and 1 state. So that's why we have a special system, a special regulation system in order to have the laser that regulated with the proper frequency, because that is very important and sometimes difficult to get. And also here we have some optical circuits. I mean, these are just mirrors and other more complicated stuff. But something important is this uh, AOM, and this is just a acoustic optic modulator. I mean, this is the AOM, it's an acoustic optic modulator, and we have uh, various of them. We have one here, one here, one here, another one here. And basically, this is a device, electronic device, that make us being able to change the frequency of the laser, and also the to control the time pulse, the time of the pulse. This is just this is here is just in order to do that, and for sure in order to also understand what is going on in here is something complicated. But the idea is that we have here our ion trap. We have atoms of lasers entering mainly in this direction here, right? In this direction, because this is the set axis in our trap. I haven't said that. And so all the lasers mainly they are entering the trap in this direction. Yeah, and we have this acoustic optic modulator that help us in controlling a little the frequency, and also the time of the pulse in order to move along the Bloch sphere, right? Finally, we have some results here. Maybe I'm not going. Oh, I didn't even translate it. Fuck. This is a sideband spectroscopy, right? This would be a spectroscopy, right? Sideband spectroscopy. So sideband spectroscopy is just trying to remember this the tuning. So using the tuning, try to find the carrier transition, right? That's a transition that we were discussing. And these are also the other lateral transitions that I have also discussed a little when you have delta equal plus minus this frequency. So in here, what we are seeing is just the excitation probability. This is excitation probability. So that means that when we have delta equals 0, we are properly excitating the electronic state, right? So when we have nothing, it means that we are using the laser, but nothing is happening to the electronic to the outer electron, because it's not the proper frequency, right? So that's what we have here. This is experimental result that we got a few months ago, and also these are some tries of measuring the radio frequency, but this needs improvement because I mean, in order to move to measure the radio frequency, we should be expected to have some oscillation like this, right? But something like this is not what we have in here, and this is mainly due to experimental errors. Yeah, I mean, well, experimental error, and also because we have just performed this Doppler cooling, but we were not able to do the sideband cooling. And sideband cooling is a little more complicated cooling procedure, but it will be good. I mean, it will be, in fact, it will be needed to do this sideband cooling in order to improve this result and finally be able, because with this experimental data, we were not really able to measure experimentally the radio frequency because we need more, another behavior, right? I mean, we cannot get any kind of information about this, right? And yes, I believe that was everything. I know it's being tough. I guess I really didn't have that much time to explain all the details, but I mean, it wasn't also my idea. The point was to just give you an idea of how this works and how complicated can things get in quantum uh, computing hardware, right? Because this is going to the hardware stuff, and think that all that I have discussed, the Hamiltonian things, quite complicated, but this is just for a one qubit, right? This is just for one qubit in an ion trap, so it's complicated, right? But that was all. So this should be the very end of this lecture series. So I hope that if you have gone through all the lectures, I hope that you have fun and have understood and learned a lot. That will be, I would say, everything from me. So thank you for listening. Luck on everything. Keep keep learning, right?